Hello, my name is Rohan Bansal. I am currently a senior.
My name is Toyesh Medikana, and I'm also currently a senior.
My name is Victor Rajesh, and I'm a senior.
Hi, my name is Akshay Murthy, and I'm also a senior.
I'm Abai Murthy, and I'm also a senior. We are Team 19018 from Liberty High School in Frisco, Texas. McKay Coppins. McKay Coppins is not a gambling man by nature. Matter of fact, he's a Mormon. He really shouldn't be betting at all. Yet he still does. Every week, he sneaks away from his wife and kids, pulls out his phone, and places a $500 bet on his favorite football team. And just like that, he's fallen into a trap which nearly a quarter of all American adults fall into, a game which 80% lose, and an industry that's profited over $1 trillion off Americans. Sports gambling. We'll return to McKay later on in this presentation, but more importantly, it's stories like his that demonstrate that quantifying the threats of online sports gambling isn't a mere mathematical exercise. It's actually a social and economic imperative. With that, I'll pass it on to Akshay to begin Q1.
So our first task was to build a model that took an individual's information and then reported their disposable income. So our model relied on three key assumptions. First, we assumed that essential expenditures were the following categories listed above. We also assumed that essential expenditures were uniform within a state, yet varied across states, and also varied with an individual's age and income. Finally, we assumed that taxes could be modeled using the 2024 US system. So the basic framework of our model was that we took an individual's gross income, then we subtracted taxes, and then we subtracted their essential expenditures. And we did so using a cubic spline framework along with Engel's law, cost of living index scaling factors, and a tax engine. So here is our model formula for disposable income. You can see that we take the gross income, Y, and then we subtract taxes, T, and then we subtract essential expenditures, which we model as the gross income times the total spending factor, which we denote as S sub S. Now let's take a look at the expenditure component, which is the S sub S. So there are two main principles that guide how we create this component. First is Engel's law, which states as an individual's income increases, the spending ratio for multiple categories actually decreases, creating a sublinear relationship. Next, we have economies of scale, which states that for particular categories such as housing and utilities, a household size of 4 may not necessarily spend 4 times as much as a household size of 1 for that category. So now, going into how we calculate the spending factor. So we first naively predict the spending ratio as a function of age only by fitting a natural cubic spline through the spending categories that were given to us in the BLS age data. So we denote this as S hat sub I of A. And you can see here the healthcare and the insurance spending ratios versus age graphs, and you can see they're highly nonlinear. After that, we adjust this initial ratio with income using Engel's law. You can see here with this formula, if the income is greater than the average income, then the spending ratio will decrease, and vice versa. And we take the average income as $96,210 as per the average of the BLS data's incomes we were given. And then for the Engel elasticities, or the gamma values, we actually calibrate them arbitrarily because of the fact that we were not given enough data to actually fit the values. And here you can see the total food expenditures versus income for a particular age, for a particular fixed age of 30 is sublinear, as we want it to fit Engel's law. Finally, we applied 2 more adjustments. We applied a household size scaling factor calibrated with economies of scale, and we denote that as phi. And then after that, we also apply a cost of living index multiplier, R, which basically accounts for interstate variation amongst different states. For example, in California, goods will cost much more than they would in another state like Kentucky. Applying all these factors together multiplicatively, we get the final spending ratio for a particular spending category. Then we sum up all these spending ratios for all the spending categories which we deem as essential expenditure spending categories. And from this, we get the total spending ratio of one's gross income on essential expenditures. Now I will let Abai talk about the tax component of our model.
Our tax component has three main aspects: the federal tax, the state tax, and the FICA or payroll tax. Because in America, the federal and also most state tax rates follow a progressive income tax bracket system, we use a summation function to appropriately model this. For the FICA tax, we use a 6.2% tax for Social Security, and that's capped at an income of $168,600. And then we also use a 1.45% Medicare tax, which is tax on all income. So that concludes our model. And then when we apply this model onto 5 unique profiles, we can see our disposable income estimates on the second table in the column D, and they all seem fairly reasonable and realistic. We then were curious to see how sensitive the essential spending was to the Engel elasticity parameters. And when we jittered Engel elasticity, we found that this essential spending remained fairly stable. It only varied by around plus or minus $1,500. So to conclude our discussion on Q1, I would like to address some of the strengths and limitations of our model. The primary strength is that we made intentional choices to include economic and theoretical backing, which means Engel's law, economies of scale, and the Colli adjustments. Additionally, it's empirically grounded through the BLS data, serving as an overall guideline, but it's also individually adaptable, as we included many personal factors such as household size, home ownership status, and also the state which you live in, amongst other factors. Some limitations are that the Engel elasticities were pseudo-arbitrarily assigned, and this was because there's no proper data set on these. And additionally, our model fails to account for any intrastate, urban, and rural variations. I will now pass it on to Vikshar to start our discussion about Q2.
So question 2 tasked us to create a model that estimates an individual's annual sports gambling outcome based on factors such as their demographic and disposable income and other key assumptions we made about the general population. Those key assumptions can be indicated on this slide. First, we model participation probability and wagering volume as independent factors. Then, we assume that there exists a base house edge that no bettor is able to reliably beat. The third one is that risk tolerance decays linearly with age, and the fourth one is that betting frequency and wager size are stationary throughout the year with no escalation modeled throughout the year in order to simplify the model. The model itself is 4 stages. First, we calculate the probability an individual is going to gamble, and then we found out their effective house edge, which is a function of their risk tolerance, which is in turn determined by their age. Then we use those 2 values in order to calculate the annual handle for an individual, which is how much they bet on sports gambling in a year. And finally, we perform a Monte Carlo simulation for the individual in order to get the outcome spread of their results. First, let's talk about this demographic participation model. We use logistic regression based on 3 factors: gender, age, and race, in order to determine the likelihood that an individual bets. We use logistic regression because we wanted to obtain a 0 to 1 very interpretable value that an individual actually bets. We use odds ratios within this logistic regression in order to understand how much more likely an individual with a certain demographic factor is likely to bet compared to the national base participation rate of 19%. These factors combine multiplicatively in log odds space. In here, you can see the formula we use for an odds ratio for a certain demographic factor, and we can see the odds ratios for each factor. Now that we know whether an individual is going to bet or not, we now need to calculate the odds they're up against, or their effective house edge. Sports gambling is not a monolith bet. There are actually many types of bets within sports gambling, which are either more riskier than the next. In order to find out what type of effective house edge a person has, we construct a function based on their risk tolerance, which is a linear interpolation between 2 portfolios. One which is fairly conservative with low-risk bets, and one which isn't conservative, focusing on the high-risk props or same-game parlays. This tau, which is a risk tolerance, is derived from 3 questions from the Siena survey. We min-max normalize these survey values and then linearly scale these values in order to match a population-weighted mean risk tolerance, which was derived from the 9.2% average sportsbook hold. We then take these 4 age group buckets and then fit a linear decay model through these points in order to get a general equation for the risk tolerance based on age, with standard errors less than 0.1 for both tau reference and k. Now I'll move on to Rohan to explain the rest of question 2.
Now that we know how likely someone is to bet, we need to figure out how much they bet. This is the annual handle, or the amount of money a person bets over the course of a year. This is our formula. We take the number of bets times the wager size, we multiply this by a risk tolerance multiplier, and then by an income scaling factor. The income scaling factor is where Q1 connects to Q2. So someone with more disposable income bets more, but we clip this from 0.3 to 5 to prevent unrealistic extremes. For the other two variables, we don't just guess randomly, we draw directly from survey data. For both of these, we randomly sample from the given probability distribution for each of our simulated individuals. With all this in mind, let's write the final formula. The annual betting outcome, X, equals -h times the house edge plus a noise term, epsilon. The negative sign shows that there's a negative outcome loss. The noise term epsilon is derived from a normal distribution. Since bets are individual events, taking them across multiple gives you a normal distribution according to the central limit theorem. These are the results of our model. As you can see, participation probability ranges from 5.9% for a professional woman all the way to 57.7% for a mid-career man. Additionally, the spread of annual outcomes shows that 64 to 71% of bettors lose money. We validated our model in 3 key ways. First of all, we anchored it to the national sportsbook hold of 9.2%. Additionally, our gross revenue, along with our loss rate, are consistent with independently reported industry figures. For strengths and weaknesses, our biggest strength is the full distribution of output according to the Monte Carlo simulation. Additionally, our model is empirically grounded with real-life data. However, our limitation is the stationary assumption. Because high-risk bettors often use parlays and non-independent bets, we actually underestimate the tail risk for heavy gamblers. Lastly, we only use 3 demographic factors. We fail to account prior gambling history and other such important effects. Now I'll hand it off for Toyesh for Q3.
So question 3 asks us to quantify the impact of sports betting in a way that is understandable to the general public. This is essentially a communication problem. The core insight is that sportsbooks like DraftKings or FanDuel are engineered to make gambling seem like entertainment spending rather than wealth destruction. And the user interfaces of these sportsbooks are designed to make users fall into the infinite trap of gambling without the average user ever noticing. Our goal is to make them notice. Our key assumptions may be concised into the following 3. First, foregone gambling losses would have rather been invested in the S&P 500. Second, any betting behavior is assumed to be stationary over a given investment horizon. And third, bettors consider financially at risk if their total losses exceed 5% of their disposable income, a significant amount. Our model has 3 phases that we assumed it to. First is an opportunity cost model. The second, a future cost disclosure act. And the third, a targeted awareness campaign targeted directly at these at-risk demographic profiles we identified back in Q2. Now, our opportunity cost model uses the future value of an ordinary annuity equation. And when we take the median bettor who bets $750 a year and plug that into our equation, we get an almost $60,000 gap that they would have gained were they investing in the S&P 500, assuming a 6% annual return. And from research, we find that 31% of bettors believe that gambling is a future investment, showing how this is a valid comparison. When we take our opportunity cost model and use it for the 5 demographic profiles we used back in Q2, we see how the opportunity costs range. However, when we take this to the national level, we see the true scale of almost $1 trillion in opportunity costs using $13.7 billion aggregate bettor loss in 2024. When we jitter this using sensitivity analysis, we see how at minimum it is at least $750 billion loss nationally, a significant amount. So to prevent this, our policy recommendation is a Future Cost Disclosure Act. We will implement this warning in green, present before any bet that a user places on a sportsbook. And this is mandated based on previous mandates such as food calorie labels or health tobacco warnings that have worked in the past to be proven. And the final step is a social media campaign. We'll target these graphs and models like this that show the true wealth gap, such as how you would gain almost $60,000 if you were to spend your money invested rather than gambling, to prevent these sorts of gamblers from even gambling in the first place. Now, to summarize quickly, in Model 1, we model nonlinear essential spending using cubic splines and adjusted this using Engel's law, cost of living, and tax adjustments. In Model 2, we used logistic regression to find the probability that better bets. Then we used a Monte Carlo 10,000 iteration simulation to find that around 65–70% of bettors lose money annually. And in Model 3, we took this to the real world and found that there's a national $1 trillion opportunity cost and recommended a future policy act to prevent this. Now, going back to McKay, who Abai mentioned, imagine an alternate scenario where he sees the social awareness campaign that we put out, the model that he could have saved, and he thinks of his child's education funds and his wife's retirement savings, and instead of gambling, he decides to put his phone away and stop gambling for good. Thank you.
Great, thank you. Does anyone want to kick us off? Yeah, go for it.
Absolutely, yes. I have a question about Model 2, perfect slide. So you use logistic regression to predict betting participation, and the variables you used were age, race, and gender. My question is, why those variables? Did you consider other variables that you didn't include in the model? And then how did you make that decision?
So we considered gender, age, and race because those were factors, or those are numbers that were available to us through the survey. And these are the only factors we considered. I think other factors such as like how exposed they are, geographic terms could also be considered in the probability to gamble. Also how much they use social media or how much you're seeing ads for like FanDuel or prediction markets for sports betting and other platforms. These are factors that we would have considered if we had more time.
I would also like to take this opportunity to address a limitation of our model. By modeling gender, age, and race independently, we actually end up dramaticizing the odds ratios. For example, some people have very little ones, while, for example, a young African-American male is going to have an explosive odds ratio, even though it might not actually be true, because these components are highly correlated.
Okay, good. Just take a second. So with the variables that were provided, with logistic regression you created, did you look back at how significant each variable is to the model? Like, what's the significance of the variable? In other terms, if it were linear regression, did you look at the correlation coefficient?
I think that's definitely a great next step. We did not look at each individual thing on its own. For example, you could use a Granger causality to see how that is. However, using our data, the test samples we were given, we could see how race specifically played a big part. The mid-career man, even though he's not in the youngest demographic, still had a high risk probability. And we think that's because race serves as a good proxy for other socioeconomic factors.
Okay.
So that's a potential way we could analyze the different effects of each variable.
Okay. Yes, absolutely.
So to follow up on what you're asking, one of the factors was age, and you had a number of cutoffs. How did you determine those cutoffs, and what would happen if you changed those cutoffs?
Could you be a bit more specific on which cutoffs you're referring to?
We just skipped. Yes.
Yeah.
So these you're referring to the age groups. These were the age groups that were from both the BLS data and the Siena survey, and that's where we got the age groups. And you can see the reference age is 26, because if you can go to the previous slide, the youngest age group, the midpoint was 26 years old for the 3 answers for the survey.
So you have two cutoffs. Well, this starts with 18 to 34, and the slide before we've seen 18 to 24. So these are very different groups.
Yeah, and that's a great observation, and it just comes down to the data we had in the surveys. Both the Siena and the Bureau of Labor Statistics didn't use the same methodology, so we got different age gaps. So by using the 26 as a reference age, we were able to take the Siena data that was in the bigger age gaps and essentially approximate what would be the values for the age gaps in the Bureau of Labor Statistics, since that's where most of our modeling came from.
Okay,
I have a related question, but for part one, because as we're discussing, like often the model is governed by what data you have available. And one thing you brought up for part one is there are these gamma coefficients on the angles curve that'd be wonderful to have some more information on. I think you said you sort of arbitrarily chose them. What data would you have needed to determine these gamma coefficients?
Yeah, so I think one piece of data that we didn't have that would have been great to have for this to determine gamma would be like if we had like a constant age, right? The like distribution of income or like the income as a function of age, not as a function of age, just like age is constant, and then we have income and then spending. So like we have spending as a function of income, and therefore we could use some sort of regression to fit gamma. But in the data we were given, we were always given age and a particular income. We were never given an income with the same age. Yeah.
Okay, that makes sense. So like if that data was more broken down, maybe you could have done a fit. And
Yeah.
suppose you did have to fit it, how would you have done that? Say you had that data, how would you have carried out figuring out the right values of gamma?
Sorry, could you repeat that?
Suppose you did have that data, like you had the fully broken down data, age, income, spending. How would you then go about determining a gamma value?
Yeah, so then we would go about probably using regression. Like you could take the log of that value and then have the gamma come out front and then try to fit that gamma value using linear regression.
Yeah, perfect. That's what I was looking for. Thank you.
So in your third question, you were looking at the total differences in opportunity costs and gambling costs. But at the same time, for your different categories, there's different disposable income levels for different categories. So just looking at the differences isn't necessarily looking at the impact it's going to have for an individual in terms of the impact on their disposable income, what's left. Just looking at the differences, if somebody has a lower income and lower disposable income, the differences by themselves don't necessarily tell the full story.
Yeah, and that's why for our at-risk classification, instead of comparing the opportunity cost to the other simulated individual's opportunity cost, we compare it to that own individual's disposable income. And if it's 5% or more, we consider them financially at risk. And you can see this here. We've shown that threshold, and you can see that 5% represents a good number as all the values are close to 0 or 1, but 5% is really where it explodes, so we thought that was an appropriate threshold.
Thanks, guys. That wraps us up for questions. We have 1 more minute if you would like to do any thank yous of your own. We'd just like to thank you for your presentation.
Firstly, I would like to thank SIAM for hosting this event. We all really appreciate the opportunity. Also, we would like to thank Jane Street for allowing us to use their offices and sponsoring the event. Also, we would like to thank the Frisco Public School District. This has been a great opportunity to represent our state and our city on such a big stage, and we appreciate your guys' support. I would also like to thank Mrs. Harrison, our coach, for helping us with the process and coming all the way to New York City to chaperone us. I would also like to thank Mr. Lopez, our economics teacher, for teaching us some of the economics concepts behind the model we used. And lastly, I would like to thank all the friends and family and siblings watching at home for supporting us through this whole process. Thank you guys so much.